Okay, good afternoon. Sorry for the delay. Okay, so let's get into the lectures. I'm going to very quickly actually, go through the rest of the slides from the introduction, and then move on to the second lecture on operating system concepts. Okay, if you have any questions from the previous lecture, make sure to ask, and then I'll answer. Okay, so we discussed about why operating systems are interesting, the fact that they're everywhere, especially in this modern day and age. The cloud computing is basically taking the world, and at the heart of it is the advances of the operating system. Okay, so I'm gonna just quickly talk a little bit about the trends in the hardware, and then I'll talk about the trend in software, and then we basically conclude this this section. So the number of transistors in our processors are doubling every year, and that hasn't kind of stopped. As you can see, this is Moore's law, and this is basically this trend, this upward trend here. However, what has changed around 2012, sorry, 23, from 2000 and around 2003, 2005, was this a slowdown in frequency. So we were able to keep our processors fast or faster as we increase the number of transistors. But then at around 2005-ish, we end up not being able to make the processors faster. The main reason for this was that we hit the power wall, meaning that as we shrinked the transistors, their power consumptions went up. And when you put transistors in a chip and turn them all on, if they're consuming a lot of power, then they could melt, and the chip could melt. So in order for you to not, burn your chip, you kind of have to put a limit on how fast your transistors could work. So this was kind of a setback. The response from computer architecture community was, okay, I can't make one processor faster, but I can put a lot of processors in my chip. So this is where we started seeing a rise in the number of CPUs in our desktops, in our servers, and so on and so forth. Unfortunately, this was not a solution. This was kind of like a backdoor. As you can see, this also plateaued, because even though we can have a lot of processors, but we haven't really addressed the issue of power. So even if you have, I right now have a server with, I think each server in our lab has 256 processors. It has two sockets, and each socket has 128 cores. So in total, we have 256 cores on one server. But this is not enough, because at any single point in time, I can't turn them all on and expect them to run at the highest frequency, because if I do so, then my server will melt. Again, because we haven't really addressed the power issue. What is missing in this graph is that around this time, around like probably even earlier, computer architects started also looking at a specialized hardware. Basically, TPU is an example. The Google tensor processor unit. It's basically, we have started making processors that do one thing, but do it really fast and with low power. So now, for instance, in this case, TPU is a processor that does tensor operations very fast and with low power. So here, when we're talking about cores, we're talking about general purpose cores that can do anything. But the new trend right now in computer architecture is to basically create these specialized processors that do one thing, but do that one thing really fast and with really low power. And you're going to see a lot of that. You're going to see a rise. I mean, it has happened. It's continuing to get to develop. And you know, there might be a time where you have a processor that runs Firefox, for example. It's kind of like a joke, but maybe you have like a processor that does really good, like it's just designed to run Microsoft Word, for example. Or somebody has mentioned something like Apple M1 chips. Exactly. So this is exactly a specialized hardware, or it has a specialized hardware. So it's a SoC, it's a system on chip, and it has really specialized GPUs for graphic, for example, operations, or for machine learning operations. A lot of now research and industry interest is going towards designing hardware that works very well in multiplying matrices and vectors, because that's pretty much what you want to do with machine learning. So if I have this really low power, highly utilized processors that do vector multiplication, I'm really good. Because that's if that's my, you know, that's 90% of the applications I do, then I can just specialize my hardware for that. And this is another reason that operating systems are important now. The rise to specialized hardware is kind of catching on to us. How do we manage now a system that has so many different processing units that are specialized? So in the past, when you have, you know, a PC that we have, it has a general purpose processor. The operating system assumes that there are a certain number of processors in the system. But in the new era, we don't have a, you know, just a bunch of processors. We have processors, we have GPUs, we might have soft processors on our FPGA. We might have this specialized hardware like TPUs. And how do we manage them? As you remember in the first lecture, I mentioned that managing hardware resources is one of the jobs of the operating system. I spent too much time on this one, so I'm going to just kind of skip over these. So this kind of shows that the performance plateaued, kind of, alongside what we mentioned. This slide talks about the fact that we have processors with many cores. One more thing, so we talked about processors. Let's also talk about memory, which is another component of the system that is very important. So this is kind of like a memory hierarchy that you will see pretty much in any computer organization course that you take. At the top of the hierarchy, you have registers. At the bottom of the hierarchy, you have remote secondary storage, like permanent storage. And in between, you have L1 cache, L2 cache, L3 cache, then your main memory, then your local secondary storage. So what is about them? So the top of this graph, the registers are really small. They have really low capacity, but they're really fast. The bottom of this, you have larger capacity, but a slower performance. So these are the numbers that you pretty much want to know. And these are relatively old, so the new numbers are probably a little bit different, not by much. So if you want to access your L1, your first level cache, it's kind of like 0.5 nanosecond. Going to your L2, that's kind of like 10 times slower. Going to your main memory, that's more than 10 times slower, and so on and so forth. The other trend that we have to pay attention to is, we talked about the trend in processor, we talked about trend in memory. I have to also talk about the trend in I/O, which is evolving very fast these days. The PCIe, now new generation PCIe 6 and 7 are coming, or 6 has come, I think 7 has come. I'm not sure actually about 7, so don't quote me on that. But anyhow, so these new protocols are coming and they're really fast. Now you have to put them all together to look at what we're getting. So it's kind of, as we saw, the processors are getting faster, but this kind of plateaued, right? The memory and the memory and I/O are getting faster and faster. One thing to not be mistaken is that the processor here is gigabyte per second, whereas the network and SSD here are megabit per second. So our I/O devices are still slower than the processor, but this gap between them is increasing. So because they're kind of linearly are getting faster and faster, but our processors are not getting linearly faster and faster. So this gap between the two is increasing. Again, I reiterate, I guess I have to say something. So sorry, I made a mistake. Let me see if I can correct that. Yeah, okay. So this one is actually, oops, this one is DRAM. This one is DRAM. These two are I/O. If I were to write, and that makes sense, I made a mistake. So both of them are basically throughput at this point. If I were to draw CPU, we'll have the same thing with CPU. So basically, I/O is catching up with both DRAM technology and also with the CPU time. So at some point, everybody was like, I/O doesn't matter, right? Because it's slow. How you manage I/O, it doesn't really matter. You can have like a dumb algorithm that manages I/O for you. But now that I/O is getting faster and faster, and it's closing the gap in terms of throughput, now people have started thinking about I/O more carefully. How do we manage I/O now that it's catching up with memory bandwidth and with the CPU clock cycle? Now this is megabyte per second. I think somebody is asking. This is mega. Yeah, I think this is megabyte per second and gigabyte per second. Okay. Now another trend here is basically how devices evolved over time. So, and then so in this figure, I have year on the x-axis, and I have computers per person on the y-axis. Now we started with having these really huge computers in a building, and everybody was just using them. So there was only one computer for a population. Right now, we are at the point where each user owns hundreds or tens of computers, right? So that's one thing. The other thing, we're still having these computer systems like data centers, where kind of like it's a big computer. It's a data center scale computer, and it occupies a warehouse, and it has millions of users. We can be, you know, Google data centers customers or users, or let's say Amazon data centers and cloud computing. So we are now at the point where both of these and anything in between, like for instance ECE cluster, it's not as big as Google data center, but it's like it has you know, has to service thousands of users, or your lab computers have to, you know, you can remotely access potentially to the same server. So our operating systems have to cover a wide range of systems. Okay, so I'm gonna jump over. This is kind of like showing the trend in software and the complexity of kernel. This is kind of showing you the number of lines of Linux kernel from version 2.6 all the way to version 4.19, and as you can see, it keeps increasing. So that our kernels are also getting more complex. Now let's put them all together. Now we have this evolving hardware, technologies ever evolving. We have different kinds of CPU architectures. We have, you know, x86, ARM, PowerPC, RISC-V, you name it. You have all sorts of different memory technologies and all sorts of different capacities. The same with SSDs. The same with network on chip. We have different IOs. So different kinds of sensors, different kinds of USB devices, printers, you name it. You have plenty of different types of IO devices. Your fingerprint, for example. Now, well, how do we, like, this is basically showing you what we're dealing with. So the hardware is complex. On top of the hardware, the applications are complex. So somebody might be, you know, just compiling code. Somebody might be using just, you know, Microsoft Word or whatever. Somebody is running machine learning applications, and each one of them is like different, and they have different requirements. Somebody might be running, you know, some a streaming application. We are in the middle of hardware and application, and we have to tame these complexities. We have to make things simple. We have to make things stable. And we don't want to really deal with the situation where we have to change the entire design every time a new sort of application comes in or a new type of hardware is added. We really want to have a modular design that would make the changes to minimum, and minimalistic changes are required. And basically, the backbone of kernel is stable, right? And we can, you know, deal with the changes as we go, without basically redesigning the kernel from scratch. Okay, so in summary, we talked about what operating systems do. We talked about how they should, how hide the complexity of hardware for the software. And basically what you should be expecting from SE350 is a combination of design and implementation choices that you can make to hide the complexity of hardware for software and bringing up a system for use and managing resources. Okay, let me answer the questions that you guys have asked, and then we move on to OS concepts. So I have, okay, have the new Apple M1 chips caused a significant change in this graph? I think the M1 chip is basically a continuation of what I was explaining in terms of the new designs that are coming. So the SoC technology has been evolving, and Mac is the latest evolution of it, and it's not gonna be the last one. And you know, Apple is in this particular position that they're designing the software and hardware together, and that gives them leverage because they can co-design and get the highest performance out of it. I know, for instance, Google and Amazon are doing the same thing for their data centers, and we're unaware of it because they're not selling it to us. But for instance, Amazon, for their EC2 services, they're designing their own I/O devices. The same with Google. They are designing their own, switches, for example, for their data centers. So they're moving towards, at some point, I remember Google was pushing this idea of commodity hardware. They were saying that we don't want to design our own hardware. We're going to go to the market, buy commodity hardware, and build up our data centers out of that. And that worked for quite a while for them. But now they are switching to this specialized hardware. So now with Mac, we're seeing it because we're the customers of Apple products. So they change the hardware for themselves and they write the software on top of it. For Google and Amazon, we're kind of unaware of it because we're not seeing it. We're just using the service, not knowing what is in the background happening. And unfortunately, most of it is similar to Apple, proprietary. So we probably never know what's in there. And the same, by the way, with Microsoft. So Microsoft, I know also for their networking and for the switches, they have moved towards a specialized hardware and co-designing it with their software. So that seems to be the trend right now. Okay, have the new cause is, okay, I guess I answered that question, megabyte or megabit. I think I answered that as well. Okay. Let's end this one. Oh God. Oops. Can you please respond? Discard. We're gonna go concepts. Okay. I'm a little bit behind schedule, so let's see. So what are we going to talk about today? We're going to talk a little bit about a brief history of operating systems, and then we start a long lecture. This is going to be probably 3 or 4 lectures. We're going to talk about threads, address space, processes, and dual mode operation. So the first kind of, it's actually not the first, but if you want to focus on operating system, there was a time that there was no operating system. So you basically had this machine for yourself. So you would, as a user, go behind this table, sit there. Your code would be written and punched on one of these papers. So this was your sort of keyboard. You would put that paper there and start put in your code and it would just, physically make holes. Then if you see this guy here, that's basically this guy. And then you wrap that around this this drum and put it in the machine, and then it would start rotating and reading your code, and then it would kind of like print the results of whatever you had. And if something would go wrong, then a red light would jump, start like flickering that, oh, something is wrong. If you wanted to debug this, it would be really hard. Let's say you wanted to compile your code, then before putting your code's punch card, you had to load the compiler. So you had to bring the compiler code, load it, the loader code, load it, and then they would come and then load your program, for example. So extremely time-consuming, not a pleasant experience, and you kind of didn't need an operating system, right? It was kind of like a serial process. We soon, this evolution actually happened very fast, like within less than 10 or 20 years, actually. So we moved from that to simple batch operating systems where instead of each user going and sitting behind the computer, users would submit their tasks. All the tasks would go to a queue. There would be something called a monitor program, which is kind of like an operating system, early operating systems. And this monitor program would dequeue tasks and then set up the machine and then run them. You usually wanted to batch your programs to have similar, for example, similar programming language, so that you don't need to load the compiler and the linker for each one of them. So you do it once and then you get done with a bunch of tasks. So this improved throughput, right? Because now, we're batching jobs and we are kind of like doing more job per hour, per day, whatever your unit of time is. But I/O was still slow. What do I mean by that? So because we had a sequence of jobs, if job 1 wanted I/O, then all of the other jobs have to wait because we're still doing job 1. So if job 1 goes for I/O, the system is just waiting. And there is nothing to be done. And then I/O comes back. We get done with job 1, we go to job 2. Now, middle of job 2, we need I/O. Again, everybody has to wait. So to deal with that, multi-programming batch OSs came to be born. And the idea behind this was, I'm not going to wait for one program's I/O. When one program goes for I/O, I'm going to switch to another program. That's why the term multi-programming comes in. And this way, I'm improving the CPU utilization. So the entire system is not waiting. So if one process is waiting for I/O, I can run another process and utilize my CPU time. Now, this addressed kind of like, CPU utilization. Now we are utilizing the resources that we have, but it still didn't, touch on the response time of the system. So your task comes in, it has I/O. Now, your task is going to wait for I/O, and the operating system is going to bring another task. But there's no guarantee when I'm going to come back to you, right? So you might then wait for a long, long time until the next process that I brought is done or goes for I/O so that I can come back to you. So the user experience still sucks, right? Because I don't have any guarantee of response time, right? Let's say I wanted to do printf. I did the printf. It wanted to go to print something that's IO. So another program comes, and this other program is like just matrix multiplication for like 2 GB of data. And I have to wait and wait and wait and wait until that's done because there's no IO for that guy. To then my turn comes if I'm not put at the end of the queue. So that led to new systems called time-sharing operating systems. So in this one, we care about user experience as well. So we kind of care about the response times that people get. And we'll talk about this and the kind of scheduling policies that are appropriate to do this. But the idea is kind of like you break the time on your CPU and you try to kind of fairly allocate that time to processes. But this requires you to kind of preempt them. So, you know, you get your time on CPU. Now I'm going to give the CPU to someone else, and then now I'm going to take it from them and give it to someone else and someone else and someone else, and then come back to the first one. And I want this to be short enough so that they don't feel like they're waiting a lot. So if the turnover is really fast, you're going to get the CPU every, let's say, you know, 100 microsecond or something, right? So that's the idea behind the time-sharing operating systems. I'm going to actually jump from this. So then, you know, this slides show you the kind of like archaeology of operating systems. And I think this meme is very meaningful because I'm not going to spend time here to do the archaeology. If you're interested, I have included actually links to like the first Unix system that came to existence. Yeah, there are a bunch of interesting links that I actually think if you're interested, you can take a look. So I included the IBM 026 key punch link. Gives you a lot of interesting stuff there. So there is this SOSP is a conference on operating systems, and they had a history day, and you can find really interesting information about the operating systems, the history. There is the AT&T, the first Unix operating system. There is the history of BSD. So if you're interested, these are really interesting talks. Some of them are on YouTube, and some of them are just for reading. So I highly recommend taking a look at that. Okay. So now let's get into the meat of operating system concepts. We're going to see in a sequence of slides the threads, address spaces, processes, and dual mode operation in our machines. Okay, let me see if there are any questions. So there's a question here. Does multiple users mean the different people using the computer, or different applications or processes that are running? Both, actually. So it could be that one user has multiple programs, or it could be that you have a bunch of users and each one of them has one program. It really doesn't matter. It means that you have a bunch of programs to run. Now, how you fairly allocate depends, right? So you can say, I'm going to fairly allocate CPU time across users. So then if one user has 10 programs, each one of them is going to be getting 1/10 of a user who has only one program. If I say, no, I don't care about users, I just care about processes, and I want to time share fairly between processes, then if some user has 10 process and one user has one, then the user who has 10 process gets 10 times more CPU time than another. So and this depends on how you want to, there's no bad or good. It just depends on the situation, which one works for you. Before actually getting into the four main concepts of operating systems, I'm going to talk a little bit just to warm up about how we boot our system. This kind of is interesting for usually for students to get a sense of how their systems are booted. And this is actually different, so based on different systems. So it's not universal, but it's just one example that gives you some sense. So usually you have your BIOS sitting in your boot ROM. In most x86 systems. So this is in a read-only memory. So although it's called read-only, it is writable, but the writing to ROM is really hard and time-consuming. So people say read-only memory. So you put your BIOS there. So again, this is expensive to write. What this BIOS does, it copies the bootloader that resides in the disk to memory. So here, let me just walk you through. This blue thingy is your disk, and this is your main memory. So your bootloader is sitting in the disk. Your BIOS goes and grabs it and brings it to the memory. And once it's in the memory, it jumps to the first instruction of bootloader. Now, bootloader then goes and grabs the kernel and brings kernel to memory. And once the OS kernel is there, then it jumps to OS kernel. And then OS kernel starts running, and what it does is starts creating processes, as we will see. One of the first ones, not exactly the first one, one of the ones that then gives the control to user is usually the login app or login process that then asks users to put their username and password so that the system can start working. Now let's look at why do we need this sequence? Why, we don't just store the kernel in ROM? Like, why did we need the BIOS? Why not just put the kernel here? So usually I would wait and ask this question to the class, but unfortunately we're in a remote setting, so I'm going to answer that. It's because you usually want to update your kernel. You don't have a static kernel for all the times, right? And as we saw, the ROM is really expensive to write to. There are other reasons for that, but this should be enough to discourage you to put your kernel in BIOS. Let me give you another reason as well before jumping. The other reason is that ROM is actually expensive, right? And kernel code is huge. So this means that you need more ROM to store the entire kernel. And that's basically not efficient. Now, okay, so you might say, okay, you convinced me that I can't put my kernel in ROM, but why BIOS doesn't go and grab kernel? Why does it need to bring bootloader? So to answer that question, the first answer is that what if you have multiple operating systems, right? How does the BIOS know which one to bring? So you want another program to give you the option. Do you want me to go to Ubuntu, or do you want me to go to your Linux machine? The other thing is, BIOS really doesn't need to know anything about file system. And what do I mean by file system? Well, in your disk, you have a bunch of bytes, right? From some address to another address. Now, how do you store files in these bytes? It's something that file system decides. So file system might, store a bunch of file one's data here, and another bunch of data here, and another bunch here. And it knows that these three are related to construct one file. So this is something that file system knows. And we'll talk about this at the end of the course, if hopefully we have time. In some years we don't. We'll see if this term I will get a chance to talk about file system in depth. If not, I'll post a video. But anyhow, now file system code resides in kernel, sort of. And it's actually like quite a lot of code to manage bytes. Now, bias is really simple. All we want to tell bias is go to this particular address and read this particular amount of bytes and bring them to the memory. And that would be the bootloader, right? If I want to bring the kernel, each part of the kernel might be somewhere, right, in my disk. And for bias to know that, I need a file system. And I don't want to do that, right? So that's why I bring bootloader. Now, bootloader is bigger than bias, so I can include some of the file system functionality in bootloader to then make bootloader aware of, where the operating system or the first file of the operating system resides, and so on and so forth. And once the operating system is fully loaded, then everything now makes sense to code to the kernel, because the file system code is also loaded with the operating system. Okay, so I got a question. I guess another reason the kernel can't be stored in ROM is because it's OS specific. So you would only be able to use OSs that work with that kernel. Okay, so this question is kind of loaded, but I'm going to use kernel and OS kind of interchangeably. They're different, right, as we talked. So let me make that distinction. I defined OS to be whatever that does what operating systems should do. And in the first lecture, I emphasized that sometimes even those system level libraries are considered part of OS. Now, kernel is a specific code that runs at kernel mode of operation, which we will talk about in a bit. So, for instance, how to do page tables, how to schedule CPU time, how to set up files, how to open files, how to write to disk. These are the codes that run in kernel mode. And anything that runs in kernel mode, we call kernel. Kernel code runs in kernel mode. But operating system is wider. Operating system includes kernel, but it also includes some other things, like you might say my system libraries are part of the operating system because they do what operating systems have to do. Now, I'm quite not following what this question means by OS specific. So maybe clarify this question, and I can probably answer that better. Okay, let's move on. Now, what is the bottom line for an operating system? Operating system has to run programs. That's the bottom line. Now, what's the sequence? The programmer writes code, edits its source code, then it compiles it. When you compile, this is really high level. It has a lot more details into it. I'm just simplifying. We'll create data and instructions. Then this is called program at this point. This is your program. Now, operating system loads your program. Here it creates a process. Now, a process, as we will see, is a running program, is an instance of your program. Again, don't worry about it. I'm going to explain it in more details, a lot more details. I have a lot of slides for processes. But generally speaking, so in this box I have the memory. So this is your memory. Operating system has its own files in memory. Now, whenever operating system wants to run your program, it brings it to the memory. It brings the data and the instructions of your program to memory. It creates a stack for you for your execution, right? You need a stack. It also creates heap for your program. This is where you do dynamic memory allocation. And as your program executes, the size of heap and the size of a stack changes. When the operating system is ready to execute your code, let's say your entire process has been created in memory, and now operating system is ready to switch to your process and start executing your program. So all it does, so this was memory. This part is memory, as I have it, mem. Now this is in process, the processor. So the processor has a bunch of registers. The most important one for us is PC, program counter. So this program counter basically shows what is the next instruction that I have to execute. And what operating system does is that it makes this guy to point to your first instruction. Once I have this, then operating system sits out, and now your program is in charge to issue instructions. Let's look at what happens when you start running your program. So as I said, PC is now pointing to your instruction. So in this figure, I have the instruction, I have the data sitting in the memory. Now PC is pointing to an instruction. I do fetch that, and then I decode it. So after I read the instruction, then I have to say, okay, what is this instruction? Is it an add? Is it a multiplication? Is it a divide? Is it a load? Is it a store? What kind of instruction are we looking at? So that would be a decode. Then once I know what instruction I'm dealing with, then I execute the instruction. So here is where you have the ALU. This basically does the multiplication, the divide, the sum, you name it. And if it was a load, then you go to memory and you bring the data back. If it was a store, you just go to memory and write it to the memory, right? And if it was just an add, then you have the result of your add and you put it back in your registers. So you're not doing anything with it in terms of going to memory. So some things to kind of make sure that everybody is on the same page. And then PC will point to the next instruction, depending on, if it was a 4, next instruction, we're going to jump again back to whatever we had in the 4. If it was jumping to a new function, then PC will jump to that new function. If it was just a sequence of instruction, then PC becomes PC plus 1, which if have 4 words, it becomes PC plus 4. Doesn't matter. So let's assume that there is the black box of PC equals next PC, whatever that be. Jumping, if it was the examples that I mentioned. Now, the question that I want to ask is how important it is for us to access memory fast. And the answer to that is very, very, very important. Why? Because with each instruction needs at least one memory reference. And that's why that's here to just read the instruction. I need to read the instruction that I want to execute. So for each instruction, I'm going to go to memory at least one, sometimes twice, right? If I have to load or store. So one is guaranteed. So for each instruction that I execute, I have to access memory. So accessing memory is very important, and it has to be done in the fastest way possible. Okay, moving on. Let's introduce the first operating system concept. Now that you know the background. Thread is kind of like a short for thread of execution. And basically, a thread is a sequence of executable commands that the CPU runs. That's basically a thread. So for each thread, we have to store a state and some local variables. Now, there is the execution state of your thread. So is your thread running? Sorry, is it ready? Is it running? Is your thread waiting? Is your thread finished? So we'll see actually different states of a thread. We also need to save a context for our thread. So basically, a context would be the registers that let's say you did an ad, and now register a specific register has the result of that ad. So that's kind of like the context of your running thread. You have to have an execution stack. That's where your function calls are happening. You might have local variables. You might have more stuff, like for instance, some metadata about your thread, how long this thread has been running. You might want to know user ID of the user that created this thread. You might want to know, for example, the priority of this thread. Is it a high priority thread? Is it a priority thread? What kind of priority does your thread have? And so on and so forth. So thread kind of like you have to attach a bunch of stuff to a thread. Now, a multi-threaded program is a program that has one or more threads. Sorry, it has more than one thread. If you have only one thread, it's not a really multi-threaded program. It's a single-threaded program. Multi-threaded programs have more than one thread. Now, your program always starts with one thread. That's the thread that runs the main function, the actual main method. That becomes the first thread. And then that thread can dynamically create more threads. As you can see in this figure, it's really arbitrary. In this example, thread 1 creates thread 2, then thread 2 fans out to thread 3, 4, 5, and then it continues over time. So at any given time, your program might have different number of threads running. Why do we want threads? Here is one example for threads to be needed. Let's say you have a user interface and you want to upload a file. If you have only a single thread, the moment you click on upload, this thread starts uploading the file, whatever that takes. During that time, it can't do anything else. It's doing the uploading, right? As I said, it's a sequence of, a thread is a sequence of instructions. Now that sequence is uploading the file. Now, if you want to abort, you want to say, no, I made a mistake, cancel. You can't, because the thread is doing something else. It's not responsive to you. To solve this, your UI thread can spawn a new thread that will handle the uploading in the background. So the moment you click on upload, a new thread is spawned, and that thread goes and uploads the file while the UI does what it's supposed to do, which is the user interface, and it's still responsive. So if you click cancel, then it can go and kill that thread, for example. So this is one example of threads. There are a ton of other examples for threads. Now, the most famous thread library in Unix systems is pthread. I got a question. Let me see. Okay, good question. So so somebody's asking, is thread 1 still running when thread 2 begins? I'm going to publish this. And to answer that question, I have to say it depends, right? Let's say if you have only one CPU in your system, then at any given time, only one thread could be running, and the rest of the threads are waiting. So that's one way to look at it. Now, let's say I have a bunch of CPUs. Let's say I have a multiprocessor, So it could well be that at the same time, thread 1 is running, thread 2 is running, thread 3 is running, thread 4 is running. Now, if your question is, what happens if a thread creates another thread and it dies or finishes? What happens to the child? I will talk about that later. So if that's the question. Okay, so another question, do we still re-app the benefit of having multiple threads even when there is only one core available? And the answer to that is yes. So that's where the time sharing comes in place, right? If you have time sharing, you can divide the CPU time between your available threads. And if this, like you give them a little bit and then you switch to another thread and then you switch to another thread and you switch to another thread and then you come back to this thread, as long as they have work to do, then from the user's point of view, if this time is divided into really fine-grained intervals, it's kind of like all of them are making progress. So even though you have one CPU, if you time share in a fine-grained manner, from the user's point of view, all of them are making progress. It's kind of like I give you the CPU, you do a bunch of instructions, and then I give it back, I give it to another one, bunch of instructions. So then somebody sitting out, they see that all of the threads are making progress. So that's where you get the response time, the responsiveness of your system. So even with one CPU, you can be creating that illusion that all of them are actually running. Yeah, in reality, you're context switching between your threads. So somebody is asking about the initial thread. I will answer this question. If I don't answer, then re-ask it later. Okay, so there are a bunch of functions that you can use to create threads. You can use. I got another question. I will answer the questions about threads and stuff later. Let me finish the discussion, and then if I haven't answered your questions, I'll come back and answer. Okay, so there is a function for you to create a new thread. There is a function to exit a thread. Now this one is important, this pthread exit. So if the main thread, the first thread that you create, just abruptly calls exit, then all the threads will die. All the threads in this process, in this program, they will die. If you don't want that to happen, then your main thread can call pthread exit. And that way, only that thread dies and rest of them live their life. And the program exits when all of them exit. Okay, now there's pthread join. So this is kind of like you say, I'm going to wait for something to happen. You usually pass the thread ID of the thread that you want to wait for. So let's say you spawn a bunch of threads to do a bunch of things, and you want to say, I'm going to wait for all of them to finish. So you join on those threads. You say, once all of them are done, then call me. So this thread join, you go to it, and then this thread changes the state to waiting. And then once whatever you're waiting for happens, then you get a signal, and then you become ready again. And then you basically get out of this function, and you can continue. Now there's a function called pthread yield. This one basically says, okay, I did some work. Now I'm a good citizen, and now I don't want to keep the CPU for myself for a long time. I'm going to yield it to others. If you have other work to do, do it. But when you call yield, the operating system gets involved and it schedules another thread. Now, this is important because it doesn't necessarily pick someone else. Let's say you're the only thread in the system and you call yield. What happens? Nothing. You continue because there is no other work to do. Or let's say you're a high priority thread and there are a bunch of low priority threads in the system. If you yield, The operating system is going to wake up and say, oh, I have to schedule another thread. Then it looks at the thread pool and sees that there is this high priority thread and a bunch of low priority threads. It's going to, again, give the CPU to this high priority thread. So again, nothing probably happens. You're going to get it. But let's say you have a bunch of high priority threads and one of them yields. Then the operating system wakes up, and based on the scheduling policy that it has, it might choose some other thread and give the CPU to them. Now, let's look at the life cycle of threads. And once I'm done with this, I'll answer the questions. So when you create a thread, you have this initial phase where the thread is being created. So the operating system, again, we're going to talk in details about how to implement this in operating system. That comes, if you look at the schedule, is multi-threaded kernels. So at the beginning, I'm just going to tell you about all of this, and then we'll talk about the implementations of it. But when you call pthread create, the operating system has some work to do to set up the, everything about this thread to be executed. So this is the initial phase of this thread. Once pthread create terminates, now I have a created thread. Creating a thread doesn't mean that I'm going to run it immediately. It just means that a thread was created and ready to be executed. So once the thread is created, it's a state. So we're now talking about state of a thread. If I go back, here I talked about threads having execution state. So now I'm talking about this execution state, to just remind you. OK, so once the thread is created, its state becomes ready. Now I have a ready thread. At some point, I don't exactly know when, at some point, the operating system decides to schedule this thread. Once the operating system makes that decision, then the state of thread changes to running. Now the state becomes running. When I get the CPU, I'm running. So the state becomes running. Now let's say I yield. If I yield, then I go back to ready. Let's say I yield and there is another thread to be run, and let's say operating system chooses that other thread, then there is a context switch. The one that was running becomes ready. The one that was ready becomes running. Another thing that could change the state from running to ready is when the operating system decides to preempt a task. For example, as we talked about time sharing, I said you want to have these really fine-grained intervals that you context switch between application. So when the time comes, operating system doesn't care where you are. It says, sorry, you're done with your turn for now. So I'm going to take away the CPU and give it to someone else. And when that happens, you get suspended. So you go from running back to ready, and you will wait your turn for another time to be scheduled on the CPU. Now, your thread might want to wait on something, right? For example, your thread could call join, or it might call conditional wait, which we will talk about later. So this will be covered when we talk about synchronization. So something to wait for, something to happen. Another thing that could happen, for example, is for you to call on I/O. Let's say you want to read a file, right? Then you kind of like go to this state of waiting or blocked. So in this state, the difference between waiting and ready is, with ready, if I give you the CPU, you can start executing. With waiting, if I give you CPU, you don't have anything to do. You're going to just wait, right? You don't have another instruction to run. For example, because you're waiting for I/O, or maybe because you're waiting for the children threads to finish. So if you wait on an event, then your state becomes waiting. If that event happens, let's say the children, all of them exit, so the children call exit, or there's a signal on the condition variable that you're waiting for. So let's say you're waiting for another thread to give you a signal that now you can do something. Let's say you're producing and somebody's consuming data, and let's say the data queue is full, so there's no more space for you to put your new data. So you could say, okay, I'm going to wait until there is a space for me. So you call this conditional wait. And then the consumer thread, when they consume something from this, then they send you a signal. They say, okay, now there is room for you to put your new item. So they send you a signal, and now you wake up. When you wake up, you go to ready. So you become ready. Now you're in a state where if I give you a CPU, you have something to do. So your state changes to ready. And eventually, this cycle could happen again and again and again. So you could go from running to ready, from running to waiting, and all of that stuff. At some point, you're done, and you call pthread exit, and your state becomes finished. There are some other transitions that I have excluded. For example, you could go from ready to finished. For example, if the main thread exits abruptly, then all the other threads, no matter where they are, they might be waiting, they might be running, they might be just ready. All of them go to finish, right? So that is excluded in this figure. Okay, I think this is a good time to answer questions. Let's see, starting from the beginning. But doesn't the initial thread have to run throughout the whole time the program is running? Not necessarily, right? So your initial thread could be just spawn 3 threads and then exit, basically called the pthread exit. So it spawns 3 threads and say goodbye, bye bye, I'm gone, I'm done. So you don't necessarily need to keep running that thread for the system to function, right? It's really arbitrary how you want to design your system. Okay, I'm a bit confused about how the threads look in memory. I will actually talk about that when we talk about address space. So that's where we talk about the memory layout of threads. So keep your question. If I don't answer it later, ask it again. Oh, that question had some other stuff in it. Where did it go? Sorry, it disappeared. Okay, so are threads and fork system calls related concepts? No, they are similar. Forks are for processes. I have a slides. We'll talk about forks, and threads are about threads. So conceptually, they both give you concurrency, but different types of concurrency, which we will actually talk about. What happens when a child thread calls exit? That child thread exits. Nothing really special. Just to clarify, is joiner a thread that is waiting for child threads to finish in order to join? So the join thread, the join function, when you call it, you go inside the function, and then you don't come back from it until others that you're waiting for them to finish, or the event that you're waiting for to happen happens. At that time, you become ready, and then you get out of the join function. So whichever thread that calls join is going to be suspended if the event that it's waiting for hasn't happened. So you go to suspend until that event happens, then you come back and become ready again. How is thread priority determined? Well, that's system dependent, but usually the one that creates the thread, they also set their priority. In Linux systems, in Unix systems, usually threads get the priority of their parents. So whatever parent's priority was, the new thread inherits that priority. Are threads and processes the same thing? No. That's why the first concept is thread. The third concept is process. We'll talk about processes. Why doesn't the thread go back to running after it gets out of waiting? Because you might be running something else, right? So it's not necessary that when the operating system has to say who gets to run, right? If somebody sends you a signal, it just says that you don't need to wait anymore. Now the event that you were waiting has happened. So now you're ready. When you're running depends on what operating system decides who to run next. So you just become ready, and if operating system wants to run you, then operating system runs you. So you don't have a say in that. What happens exactly when multiple threads are running? Is the program ready reading an instruction from one thread, then the next, and so on? So that depends on how many processors you have. So if you have one processor, then at any given time, you're just running one thread. But if you context switch between them so fast, then you kind of give the illusion to the user that they're running, they keep running, right? But at any given time, you're fetching an instruction from each thread if you have one processor. Now, in a multiprocessor, where you have a bunch of processors, then you can fetch instructions from different threads. So in actuality, you're actually running a bunch of threads at the same time. You're fetching instructions from a bunch of threads. So the answer to that question depends on the number of processors that you have. What is the difference between a process and a thread? I promise I will clarify that. For now, let's talk about threads, and then we'll come to a process. If I want to just in one sentence, a process has one or more threads. It has other stuff, which we will talk about. It has also a memory state. So that's why I'm delaying the answer to that question. If a thread has children running and exits, its children don't get terminated, right? Depending on how that parent thread terminates. If the parent thread calls exit, all the children die. If that parent thread calls pthread exit, then it dies itself, but the children get to execute. Another question, are threads grouped by process or are they organized by a hierarchy? Does calling exit on a... So for the first question, it depends on the operating system. So different operating systems have different ways of categorizing threads. Usually in Unix systems, they're categorized based on the process, right? Now, what that means exactly depends on the scheduling policy and all of that, right? But in general, you want to treat the threads for each process. If it has 10 threads, you want to kind of like treat them equally. So you put them all in one group. Does calling exit on a child thread terminates the entire process? No. Or just it's just the children. So the children that calls exit exits, not the entire. Actually, that's a good question. I might be wrong. I have to verify that question. I don't know. So I think I have said it a bunch of times now. I'm not sure. Let me check. I think if I might be wrong. So it might be the case that whichever thread calls exit abruptly, the entire process exits. That might be true, actually. So whoever calls exit, then the entire, process dies and all the threads die. But I have to verify. I'm not sure. And it could be a convention, like there's no right or wrong answer for that. How does the OS take back control when it wants to suspend? I will talk about that. Keep that question for when we talk about dual mode operations. Just to clarify, when a parent calls exit, do all the children exit as well? Yes. They all die. They all go to finish. Okay, so what does the operating system keep for each thread? So usually the operating system creates this control block per thread. It's called thread control block. It's called TCB. So a bunch of information that operating system keeps for each thread is basically the TID, the unique ID of this thread within this process. As we talked, each thread needs a stack. So the stack pointer of this thread, the program counter of this thread, because it's kind of like a sequence of instructions. So we want to know what was the last instruction we executed from this thread. So what is the program counter? We want to know what's the state of the thread. Is it running? Is it ready? Is it waiting? Is it finished? You might want to also keep the registers. Let's say if the thread is not running, let's say the thread is waiting. So you want to know what was the state of the processor when it was running the last time. So whatever it was in the registers, the operating system wants to save them somewhere so that when we come back to it, we can change the state of the processor to what it was before, and then we can continue running. So you save those registers in the TCB. And by the way, TCB resides in memory. So it's a data structure that operating system keeps for each thread in the kernel memory. And then eventually you probably want to, actually there are more, as I said, about like priority, for example, how much time this thread has run, so on and so forth. But also you probably want a pointer to the processor, to the process that this thread is a member of. So each process, as I said, has one or more threads. So you probably want to include a pointer to the process control block. Now we're talking about thread control block. We will soon talk about process control block. So a TCB can have a pointer to the process. Some numbers. This is my system. I think from 3 years ago. At the time where I took this screenshot, in my system I had 2,067 threads running, and the number of processes in my system was about 445. So this actually shows you that Firefox, for example, has 69 threads. Thunderbird has 61 threads. This not very pleasant program has 142 threads, and so on and so forth. So you usually have a lot more threads than you have processes, because each process has one or more threads. Yeah, okay. Since I started this lecture late, I'm going to go a little bit over time. So if you have to go. The lectures are being recorded, so you can come back and watch the end of the lecture. So sorry for being late and having to go over time. Now, the second OS concept, so the first OS concept that we talked about was threads. The second OS concept that we're going to talk about is address space. What is it? Before we jump to address space, what is it? What is an address space? An address space is a set of accessible addresses and what is in them. So an address space is a bunch of addresses in memory and their values in those addresses. So that's an address space, very general definition. Now let's distinguish between two things. One is physical memory. This physical memory is basically the memory that you have on your system. Let's say you buy a laptop and it has 4 GB of memory. This is your physical memory. There is so for a physical memory, you have a physical address, physical addresses. So these are the addresses for each byte of your physical memory. So byte 0 has address 0, a byte 1 has address 1, byte 2 has address 2, and all the way to byte n has address n. And then you're probably storing something in that address. So the address and the content, That would be your physical address space. Now you also have virtual address space. Now what is the virtual address space? Has nothing to do with your physical memory. Virtual address space is a virtual memory. And we will soon see that we want to map virtual memory to physical memory. Now you might have a system that has only 4 GB of physical memory, but then your virtual memory could be terabytes of memory. You might have terabytes of virtual memory. So this is a memory that is accessible to the program virtually. But then at some point you have to map this to your physical memory, which is the second part of the course, which happens after the reading week. So we will start talking about address translation. That would be translating virtual address to physical address. So a bunch of numbers. So if you have a 4 GB memory, then you have 2 to 32 bytes, right? So basically you need 2 to 32 different addresses. To be able to address each byte. Now, if you are running on a system that has 64 bits, most of our current computers are 64-bit computer. Old computers were 32 bits. So in these processors, a processor that has 64 bits, how many different bytes can you address? Well, you can address 2 to 64 bytes. And that's usually your virtual address space. So as you can see, this is basically a lot more addresses than your physical memory can provide. That's why we usually want to map virtual memory to physical memory. And if you're running a bunch of processes, each one of them has its own memory. So it's not just one huge virtual memory that you have. You have, in this example that you saw, you have 445 processes. Each one of them has its own virtual address space. But then in my system, I probably had 4 GB of physical memory. So I have to find a way to map all those virtual memories to physical memory. OK, so let's stop here. This is a good starting point. Stopping point. Sorry again for going over time. I apologize for starting the lecture late. I have questions, so I'm going to answer the questions and then end the lecture. So could it not depend on the implementation of the program? Like if you kill a Chrome tab, that doesn't just kill the entire browser, right? Yes, it doesn't. So as I said, if you want just your thread to terminate without affecting other threads, you can just call pthread exit. I think the question was, what if you just call exit on a thread? And I think I have to verify that. I probably will do so in next lecture, telling you if any of the children threads calls exit, what happens. I have a sense that probably the entire process will terminate, but I have to verify. And that could actually depend on system. So it could do something in one distribution and could do something else in another distribution. I don't exactly know. So for example, Linux could do it differently than Windows. I have to verify. Or maybe not. I think we have to verify it with POSIX standard to see what POSIX says. So I'll do that for the next time. So what's the TCB data structure? A hash map. That depends on how operating systems implement TCBs. So Linux could do it differently, Windows could do it differently, Mac OS could do it differently. That's the design choice that the operating system makes. Usually, in labs, actually, the labs that you're gonna do, you're gonna have a TCB, and it's kind of like a simple struct, a C struct. Now, how you then put bunch of TCBs for different reasons, you might want to create lists of TCBs. Then you can think about fancy methods to sort your TCBs, right? For instance, if you want to have a ready queue, meaning that the queue of ready threads, and if you look at Linux scheduler, they use B+3. No, actually, they use red black tree to sort the TCB pointers. So if you have a bunch of TCB pointers, these are the threads that are ready to run, and you want to kind of like have a data structure to store them, then you might want to use, fancy data structures. Because again, for scheduling, you want to be able to pick the next thread really fast. And the way that is done in Linux completely fair scheduler, CFS, is by putting all these pointers in a red-black tree. When is Lab 1 going to be released? Soon, hopefully very soon, probably today or tonight. You have to talk to Irene on that. Maybe ask a question on Piazza. What are pthread functions defined? What are pthread functions defined through? Are these C functions? So there is an API in these are C functions that you can use, but then under this is like basically another thread system library. Eventually, they will be implemented in assembly or something like that. So in ECE 350, students actually implement these functions. So I think in SE 350, we kind of give you, but we ask you to do a bunch of other stuff. But in ECE 350, students actually implement these in sort of C language and a little bit of assembly. Okay, so that's it. Thank you for those of you who stick around even 9 minutes after the deadline, after the end of the lecture. Again, sorry that it took long. Take care, be safe. Talk to you on Thursday. Bye-bye.